All right, so it is 3:30. So I'm going to go back and just quickly finish up the step 3, these special forms, the def, bang, and the let star. All right, so as we mentioned for the def, one of the things I forgot to mention is that it returns the value that you defined also. So what I'm going to do here is in our current environment, I'm going to update one of the, or possibly create a new setting. I'm going to use the first argument. So let me just put an example here. So in this case, the second element of AST is that ABC symbol. So I'm going to set in the environment ABC to the evaluated value of the second element, and then return the result. The return result is just going to be the way we defined set, returns the value that we set it to. So this value is going to be set in the environment and returned. So I can actually have a look at that. So I haven't implemented let yet, but I've implemented def. Okay. So now in our current environment, we have a new binding for ABC that is 1, 2, 3. Now if I did, one of the key things is that if I do this, the updated value of ABC is the evaluated value. It's not that literal list. We evaluate that second argument first before we set it in the environment. And that's what this does here. That part right there is evaluating the body of the def. And then we use the first argument, unevaluated. So here's an example where we only evaluate part of the list, not the whole thing, because def is a special form. And that's one of the sort of fundamental natures of special forms, is that the special form gets to decide how its arguments are evaluated and in what order. Okay. Just as an example. All right, so how are we going to do this one? So the first thing that let does is create a new environment. Its parent is the current environment. So then what let does, oops. Okay, so I'm gonna iterate over all the values in all the odd values in the binding list. So those are going to be the symbols, that A and B in the binding list. So then I'm going to take our new environment and I'm going to get that element, that symbol from the binding list. And I'm going to evaluate it in the context of that new environment. This is a key functionality that we need to do here. We're building up an environment, and we can refer to earlier bindings in that environment as we build up the environment. And then the final thing we do here is we evaluate the body of the let, so the star AB, and I did this wrong. We evaluate it using that new environment. And you'll notice here that we're not, once the let is gone, once the let finishes, this new environment that we created, we're not saving it anywhere, so we discard it, so it goes away. Gets garbage collected in this case. Okay. B plus 1A. Let's do 10 plus B. Oh. Required position. Yep. So there's an eval here that is missing. Oh, too many parentheses. Too many parentheses in my Python code. All right. Just make sure the very simplest example works. Make sure that we're properly evaluating the body of the let here. And then also make sure that we're evaluating the basically the right-hand side of the bindings, the even position. So let's do that. Okay, so A was bound to 7, B was bound to A plus 1, and then the final value of the let is B plus 1. So that's why we have 9 there. Okay. So that's step 3. So I am going to go on to the next step, but oh. Oh. Okay. Alrighty, let's talk about step 4. So this is where things really start to get interesting. Not harder to implement, so to speak, but we after step 4 we're beginning to have a real Lisp language as a result. So what we're going to add in step 4 is conditional support and function closures, and also some core functions that do side effects. For this step, I'm actually going to go through fairly quickly because it's a big step with a lot of stuff. So I'll try and pause and give a few minutes here and there for hands-on, but we are a couple of minutes behind. So let's see here. Okay. All right. So as you can see from the red here, in the upper left, what we add is this new namespace called core. We're going to move our functions. We have plus, minus, star, and divide. We're explicitly putting those in. We're going to move them into a namespace along with some other functions that we define, and I provide those for you already. In the evaluator, we have 3 new special forms: do, if, and fn star. Do is a way of combining several different steps together, and the reason you'd want to do that is because you have side effects in your steps, and I'll show you that. Then if is kind of self-explanatory. We already talked about that in the crash course. That's basically our conditional, and then fn star is how we define new functions, new anonymous functions, closures, or lambdas, since this is LambdaConf. Let's see here. Okay, hold on a second. All right, so the first thing I'm going to do is just go over these core functions real quick. So this is I'm just creating a dictionary in the core.rb file. You should have in the workshop repository. You should have a core.rb, core.js, and a core.py in your already there. That's defined for you, because these functions really aren't Lisp per se. They're just functions that could theoretically exist in any language. The first function we define is equals for comparing two things. And again, these are normal functions, not special forms. We have 4 printing functions. The first 2 just return a string. The second 2 actually print out to the console. So they are actually our first 2 side effect functions that have a side effect. So they have a return value of nil, but they also have a side effect that they print out something. I'm going to skip those for now. Then we have some comparison operators for comparing integers. We have some integer operations that we saw before. We've copied those in here. And we have a couple of new sequence functions. So we have a function called list. And what this does is basically just return a list of its arguments. And this function, list question, by the way, in Lisp, it's fairly common to have a question mark as part of your symbol, and that means it's a predicate function that returns true or false. So this will return true if the thing that you invoke it against is actually a list and not something else. We have a function called count that will count the number of entries in a list, and a function called empty that will return true if it's a list but it's empty. Okay, and then there's some other functions that are for later steps, but okay. Okay, so I'm copying my step 3 to step 4 if fn do. I'm going to do my work in there. Make sure you get the spelling of this right so the test can find it. All right, so here's our the Ruby versions of the 2 special forms that we defined in the previous step. What we're going to do now is add, we're going to add do, if, and fun star. I quoted this because Ruby doesn't want stars and symbols, but by default. Okay, so so those are 3 new special forms that we're going to do. And down here, I'll just do this real quick. So instead of setting our REPL environment from just these explicit settings, what we're going to do actually is, well, first what we're going to do is pull in that core file. And then down here, we'll create the REPL environment, but not set anything in it yet. And then what we'll do, oops, oh, where am I here? Okay. We'll do a loop here over that dictionary in the do file. Oops, come on. So this is a Ruby-style iteration over the keys and values of that dictionary. And then, so I suppose I could split this onto different lines for friendliness. Okay, so even just doing that, we've actually given new functionality to this. So by importing the core functions. So if I so up to this point, we haven't actually had a way to do this, to actually have a list return, because when we put a list, we do this. It's going to try and evaluate that as a function invocation, and we'll say 2. You can't really use 2 as a function, basically, is what this is saying. But we created a function that takes arguments, and what it does is return a list. And so I can then use one of the other functions that we just defined in the core and test that really is a list. That's not. So just by importing that core environment and then basically inserting those values into your REPL environment, you've got access to all those core functions now. So 2 is in fact less than 3, but not greater than 3. Okay, so let me here, I'm going to go ahead and just do the implementation of the do special form, just right off the bat. So, so in do, what I'm going to do, I feel like I'm saying that word a bit too often, is I'm going to use our eval ast utility function now, but I'm not actually going to run it on the whole thing, because if I did that, what it would see is our eval ast function would see a do at the beginning. So I want to skip the do special form, and I want to evaluate the rest of the elements in that do special form. And then all I'm going to do is let's see, trying to remember my Ruby here. And then what I'm going to return from that do special form is the evaluated value of the last thing. Now, why is this interesting? Well, we could do that. That doesn't do anything interesting. But one thing we can do is have something in here that has a side effect. So this is how I would basically do a print, but return a value. I mean, I could have done 7 there to print 7 to the screen, and then return a value. Yeah, so that's the do special form. And one, yeah, don't need to say much more about that. There's a bunch of places where that's important and useful, but it's one of our special forms. And then, so for a couple of minutes, I'm gonna pause so I can answer any questions that may have come up, and let you guys. You can implement do in your own language, or copy the Ruby one if you're doing Ruby. And also the next. So for the first hand-on, implement the if special form. And so just real quick recap. The way if is going to work is you're going to evaluate the first argument, and then depending on the result of that, you're going to evaluate either the second argument or the third argument, and return the value of that. Okay.
Could you show the usage of do in the REPL again?
Yes. For those that are new to functional programming, the fact that you even need this thing called do is a bit weird. But everything in Lisp is an expression. So everything you do returns a value. And so and if when we get to, so let me just give an example of where this might be useful. So I can create a more sophisticated where in the places where you have a single thing that must be evaluated, I can create a more sophisticated thing that might have side effects, basically here. So I basically put in a debug statement into my let. I mean, here it's pretty trivial. You know what's going to happen, but this is do is one way you might do debugging. All right. Anybody have questions that I can answer real quick? Okay. So since this is a big step, let me just quickly implement how I would do if in Ruby. All right. So what we're going to do is capture the result of evaluating. By the way, up here, I pulled out some shorthands for the first 3 arguments of the AST that we're evaluating. If they don't exist, they'll just be nil in Ruby. In Python, you'll actually have to. This works a little differently, but I don't have to do this. I could have done AST1 here, but just for shorthand, I'm doing that. So I'm going to evaluate the first argument in our environment and capture the result. And then, if it evaluates to something to either nil or false, and conveniently in Ruby, only nil and false are false in Ruby. But in other languages, you'll have to be a bit more explicit here and test specifically for nil and false, because like in JavaScript, there's some other things that are falsy. You need to, and you don't want those to be false in Lisp. So if it is false, then I'm going to return the evaluation of, oh, and I need to add another convenience here. I'm going to return the evaluation of the third argument. If it's true, then of course, I'm going to return the evaluation of the second argument. And there's one other bit of functionality that's really nice to have here, which is that if you don't actually have something for a third argument, then we just return nil in the false case. And what this effectively gives you is sort of a, if this is true, then do this, otherwise return nil. But it's automatically, you don't have to explicitly specify the nil. But this is just sort of a convenience thing that I use. Okay. So that's if. Let me just, okay. 53. When missed an end. All right, so if true. So it was true, so we evaluate and return the second argument. If it's false or nil, we evaluate and return the third argument. And what I was giving the example of before is that if you happen, I added that functionality, so if you happen to admit the false case, it'll still return nil and not give you an error.
It's just like an empty string.
So, right. So for an empty string in mal is a true value. Only false and nil are falsy. So anything else is going to be a truth value. Yeah, even 0 is true.
Empty list.
An empty list is true. This is, and that's, you bring up a good question actually. In some lists, Lisps, they treat empty list and nil as basically equivalent. In mal and Clojure, because it's modeled after Clojure, these are not treated the same. But historically, the oldest Lisps, did treat nil and the empty list as sort of the same thing. Yep. Okay. So the next thing we'll talk about is functions. So fn star is yet another special form, and as I mentioned earlier, it returns a lambda, an anonymous function. And so and the way it works is it doesn't the fn star special form doesn't even evaluate as arguments at all. All it does is basically capture them and store them for later. So the first argument of fn star is the parameter list. So it captures that AB list without evaluating it. It also captures the body of the function, the star AB, as a list and doesn't evaluate it. And so that's all that special function does at that point. There's some changes that we actually have to make to the apply section when we run into a mal-defined function that's defined in mal this way. Because so far all the functions that we defined have been implemented in Ruby or JavaScript or Python. Now we're allowing you to create your own functions. And so when we call that, we need to do something special. And what that is when we call a function that we've defined, a new environment will be created just for that function call. And in that environment, the parameter list, each of the parameters in that list will be bound to the arguments that function is called with. So in this case, we have a function that multiplies a and b together, and it takes a and b as parameters. And what will happen when this function is called is a new environment will be created, then a will be bound to 7 in that environment, b will be bound to 8 in that environment, and then in that new environment we've created just for the function, we'll evaluate the body of the function that we saved from before. Now, I should point out that when I say saving here, saving the values in the special form, you can do that explicitly with an object and save it. You can also use a facility in the language that you're targeting. If it has it, you can use the Clojure functionality. Not Clojure with a J, but Clojure with an S, which means you're creating an anonymous function and it's referring to some things in its environment. So let me here. That's the second. Okay, so I'm going to just quickly, okay, there's the stub. So you can use a anonymous function, a lambda, like in Ruby, you can use a lambda, you can use a Clojure in JavaScript or Clojure capability in Python. I also do provide in Python and JavaScript, the types file has a function class that you can use to save that data off, which we will need to use later, but for now, in all three of them, you could just use a Clojure if you wanted. And then the difference is down here, we're actually going to test down here. Actually, we don't need to. If you use a Clojure, so I do recommend for this step using a Clojure from your target environment, then you don't actually have to change anything here, I don't believe. Yeah, you don't. So for the next few minutes for hands-on, let's see, how much time do I have here? Yeah, we've got a few minutes. So, probably not going to have time for that. But so there's one missing piece of functionality I forgot to mention that you'll need to be able to do the function binding. So we're actually going to add some new functionality to our environment class. Okay, so I've added to the. I'm sorry, what's that?
The default values in your initialize, should those be nil instead of?
Yep. You are correct.
Actually, you probably want empty array.
You're right, I do want empty array. Yeah, there's a couple different ways of doing this. But sometimes after having done a couple dozen implementations, I kind of confuse myself, keeping them all in my head. But okay, so what this does is we've added two optional arguments basically to our environment constructor, a binds list and an expressions list. And what we do is we basically iterate over the binds and expressions together and just assign them into this current environment, just add them to our environment. So that's just some functionality, some utility functionality that we're going to use for the definition of our fn star. So our function special form. Okay, so I'm going to go ahead and implement this. So I'm going to use Ruby's Lambda capability to create a Clojure, anonymous function here. It's going to be a Lambda function that takes a variable number of arguments. And what this Ruby Lambda function is going to do is it's going to return the result of evaluating A2, so we're capturing the second argument of the function special form. That's what we're going to evaluate, the body of the function basically. And then we're going to create a new environment for this evaluation. And its parent is going to be the current environment when the function was defined. Not when it's run, but when it's defined. It's a key distinction. So it's going to be, its parent environment is going to be where it's defined, and that's called lexical scope. There are options, but they're more confusing in my opinion, and most modern Lisps don't do dynamic binding like that. So, okay, so we're creating a new environment. The parent environment is the one we define it in. And then we're going to use the new functionality we added to our environment class. So the list of things we're going to bind is the parameter list, and what we're going to bind them to are the args. And actually, I'm not sure this is actually I think it comes in here as a tuple, so I'm converting it to a list. Okay, so just to recap, in the function special form, I'm using Ruby's Clojure LambdaConf capability and defining a new Lambda. It's not running this eval, by the way, when I do this. We're creating a new function, a new Ruby function. And what that Ruby function does is it will, when it's called, it will call our eval function using the original body of our function, create a new environment with the parameters bound to the arguments that it's called with. And that happens when it's called. You have to keep that in mind, that this eval is not happening when we define the function, but later when we call it. And so we're returning a first class function here. It captures the body and the parameters and the environment that it was defined in. So let's see if that works. First we'll see if, make sure it doesn't throw an error when we define it. And let me just so it's clear, capture that. So we have a new function now that we've defined. And yeah, so when I call that function, this code right here is being run. And notice that this is called closing over the value A2 and A1 here, because later when we actually run this, those have gone away in the context that that eval that created this function has long since exited. But closures allow you to keep references to values, and only when you get rid of all the closures that reference those values would those be cleaned up and garbage collected. But this is something that's fairly common in modern functional or programming languages that have functional capabilities. So all three languages, Ruby, Python, and JavaScript, have the ability to create closures that do this. Okay. So let's see here. Oh, and there's one more. So there's one more little magic thing that I'm gonna, not really magic, but a minor extension that I'm gonna do to this. What we're gonna do here is, as we're processing our parameter list for our function, if we come to an ampersand, I think I need to quote this. If one of our parameters in our function list happens to be an ampersand, then we're going to do something different. And what we're going to do is we're going to use the next symbol after the ampersand. And we're going to bind it to the list of arguments that we haven't processed yet. Now, why would we do this? So I'm just going to return this function. All it's going to do is return the value b, its parameter b. I'm going to change this to A. So what happened here was A, since it's before the ampersand, just got bound normally to 7. Then we see that we ran into the ampersand there. And so what we do is we take B and we bind B in our environment to all the rest of the arguments that we haven't processed yet. And so what this basically, with that small change, what we've basically accomplished is we now have variable length functions that support variable number of arguments by doing this. So I could have done this, in which case what we've basically just created is an equivalent of our internal list function, which just returns all the arguments. We could also do count. So what this function is doing is telling us how many arguments we gave. So basically this minor change is giving us variable length arguments. So let me just show you that again. So as we're processing through the bindings, if we run into an ampersand, we take the next symbol and we bind it to the rest of the arguments as a list. Okay. So step four was the biggest step. I kind of had to go through that kind of fast. None of the particular tasks that you have to do in there is really that complicated or big, but there are a bunch of them. But I will point out though, once you've completed this, you really do have, basically you have a language now. You have a real language once you've completed step 4. It's limited in many ways. You know, its core functions are pretty limited, but you can create functions. You have conditionals. You have the ability to do side effects, and so you know you at step 4, once you've completed it, you basically have a Turing complete language. So let's see, 4, 5. Yep. Now it is complete, but there's some things that are particularly inefficient about it. So one of the things you might have been wondering, you know, this is a complete language, but where are loops, for example? There is actually the ability to do iteration or recursion already defined once you've finished step 4. I didn't show it to you, but it's extremely inefficient because every time you recursively call the same function again, you're creating a new environment, right? And so you wouldn't have to process a list that's very long before you'd run out of memory, or you'd run out of stack. Your stack you'd overflow your stack. And so basically all lists have some concept of tail recursion, tail call optimization, and it's an optimization. It's not like a core thing that's visible in the language, but it's an optimization that allows you to do recursion indefinitely. So you can, if you structure your code right, you can recurse indefinitely, and that actually allows you to do loops. And so by the way, this is one of the steps where you might want to catch up if you haven't finished step 4. This definitely could be useful to catch up. Okay, so let me show you. Let's see here. Actually, I'll go back in here, and I'm going to I'm going to create a function here called sum2. What sum2 does is sums, it counts down and sums up every value as it counts down. And so if you look in this function, you'll see that I've added a conditional in the function. So the function takes one number. If the number that it got was 0, then it just returns 0. Otherwise, what it does is adds that number to another call of sum2 with a smaller value. So basically what'll happen here is if you called sum2 with 7, sum2 7 is called, then sum2 6 is called, sum2 5, 4, 3, 2, 1, and all those functions are on the stack, with each one with their own environment using up stack. And so, okay, that worked, but that didn't. So what happened is we ran out of Ruby's stack. We just have too many function calls stacked on top of each other, each one with their own environment, each one using up stack space, and so we crash. And so that severely limits what we can do. And in fact, technically, step 4 is not Turing complete because you can't do things like this. I mean, if Ruby had an infinite stack, you could, but it doesn't. So, all right. So I'm actually going to switch for this step to JavaScript. I know. Part of the reason I'm switching back and forth between languages is so that as I implement in one language, you'll need to, for the language that you're doing, you only see the steps every now and then. Yep.
Do you test pass now for the Ruby?
Oh, good question, yes. Let's see. Let's do it over here. Whoops. So That's a good question to ask. Basically, almost all the tests did pass. There were 4 that didn't, and the 4 that didn't were all related to the fact that I forgot to implement a not function, which I showed you here in the, whoops, come on. So up in the environment, you can see there's a not up there. If you can see that, it's pretty small, but, so let me do that real quick. So one of the cool things about step 4 is that, like I said, we now have the ability to create our own functions, and we can do that even in our implementation itself. So, and the way we do that is we can just call the rep function directly with a string and do any sort of So this is going to define a function called not that will reverse the truthiness of its argument. Okay? Yep. Okay. Yeah, so it not will return true or false depending on the truthiness of its argument. And it's just a function that we defined. So using the capabilities that we have now in step 4, so we have conditionals, so we can test the truthiness of our argument, and we have the ability to define new functions. And then what we did with that function is we defined it in our base environment. Because this read eval print call is happening in the context of our base environment here. So it created this, it added this symbol not to our REPL environment. Okay, so good call, by the way, on running the tests. All right, so now let's move on to TCO, tail call optimization. So in this, you can see the red here is basically, it's just some arrows. There's no new pieces here. It's just there's this sort of control flow change. And so there's basically four cases in the eval function where we have to do some modification to change the control flow. And so let me all right, so step 5, we'll switch to JavaScript. And this one is called step 5 underscore TCO. Okay, so here's our eval. And just to refresh, if it's not a list, we just do eval est on it. If it is a list, we have these special forms that we check for. And if there weren't any special forms in the first position, then we do basically the invocation of the function case. All right, so TCO basically looks like this. I'm not going to change the indenting. I'm going to wrap the entirety of our eval code in a infinite loop right there. Now, because every control flow path through here calls a return, this actually didn't change the behavior doing that. But that's the foundation of our tail call optimization. So as I mentioned here, let star, do, if, and the apply block, the else of our apply, are the things that are going to change for tail call optimization. Whoops. Okay. So we're going to make a modification here, here, in this block, and also in this area. All right. So I'm going to, let's see, how's my time doing here for 5. Yeah. Okay. We're all right. I'm going to just show the implementation of how we do TCO for the let block. So, oops. That's it. Now, so what am I doing here? So we look at if we look at the definition of eval, we have these local variables, AST and env. And the body of our let, there's no other code in here that can touch that EST and the env local variables. And so what that means, so that's the body of the let is called the tail position of the let, because there's nothing else that can happen after that. And so what I'm doing here is instead of calling eval, so what I had here was this. Instead of calling eval again, so instead of recursing into eval, our eval function, all I'm doing is I'm updating our AST value for our eval function to be the body of the let. I'm updating our environment to be our let environment, and then I'm looping. So what I'm doing here is I'm skipping the call to eval. So we're not using up any more stack when this happens. So a let now will not, when we do a let, if we had lets inside of lets and inside of lets, the body of that let, we wouldn't be using up any more stack. We'd have one eval call that's looping around to handle all the lets.
So the environment replaces the previous environment rather than becomes a child.
Yeah, and I could have done, for example, I could have done this and then skip this up here, but it's a little confusing to have env and env on the same line. I mean, this works, but I like the clarity of defining a new environment and then updating our current environment to be this. And the reason this works, again, just to be clear, is that because the body of the let is in the tail position, there's no other thing that could use AST and env again. And so it's safe to update it because nothing else will use it. And so we're reusing this stack context basically. Okay. So for the hands-on, we're going to have a few minutes of hands-on. The next, the hands-on is basically to implement. So I did it for let, and the hands-on for you guys is to implement this for do and if. And I'll come back and I'll do the function, the fn star, the function special form. So I mean you can go on to do that, but I'll jump in a couple minutes and finish that off. Any questions or trouble that anybody's having that I can answer? Yeah.
I guess I'm a little confused by how you can state with certainty that the let body is in the tail position. So I guess I'm not understanding the underlying structure there. How do we know definitively that the body of the let is in the tail position so we can make this optimization?
Okay, so instead of showing you the Lisp answer to that, I'll show you the actual implementation of Lisp answer.
Okay.
So the reason is because this return happens in front of the eval. So there's nothing else that could happen. Okay. By definition, we're going to recurse into eval and then return from our current eval, and there's no other use could happen to the AST and env values. Okay. Right. So that's the answer that didn't answer the Lisp part, but I think it's almost easier to conceive it here, what tail position means. Now, in the Lisp context, what it means is that the sum2 example that I gave is not tail recursive, which means that the recursive call to sum2 is not actually in the tail position of the if. So to get a tail call recursive proper implementation of sum2, we'll have to modify it slightly to actually have the recursive call in the tail position. Otherwise, we can't do the TCO. We have to keep those AST and env values around and actually do a recursive call. this doesn't die in the middle. Okay, so that was, that's TCO for let. So I will do, a do is a little bit odd because the tail position of a do is the very last argument. So the modification I'm going to do here is so I'm going to evaluate every argument of the do except for the last one. That's what this slice is doing here, and I don't care about the results. And then what I'm going to do here is I'm going to update our AST. There's no environment changes that do does, so we don't have to worry about the environment. It can just stay. It'll just stay the same. But our AST will be updated to. Let's see here. Yeah. So the reason I know I can do this is because we have a return here after the evaluation and nothing else. So I'm going to get rid of the non-TCO code. So the difference here is that before I had eval AST evaluating every argument of the do special form, and then returning the evaluated final position. In the tail call optimization version, I'm going to skip the last position, and then I'm going to update AST to be the last position. And so this accomplishes basically the same thing functionally. I'm going to loop back into eval and evaluate the last position of the do, but it's a tail recursive version of it. So that's do. So if so this is for if instead of, so the problem here is this recursive call to eval that we return. So what I'm going to do is well, basically I'm just going to update this and get rid of that. So this is handling both conditions where we don't have a third argument, in which case we'll return null. But if we do have a third argument, then we're updating our AST to be the third argument and looping. Specifically, we'll need to do this down here. Okay, so I'll keep that so you can see what the transformation of this one is. So here's the non-TCO version, the non-tail call optimized version, where we're recursively calling into eval and then returning the result. The tail call optimized version here, instead of evaluating it, we're just setting AST to be that, to be the true position, and then looping again to the beginning of eval. It's effectively, so again, just to be clear, it's effectively the same functionally as calling eval again. But what we're, instead of actually recursing into eval, we know we can reuse this eval context on the stack, and so we're updating AST to be the true position, and then looping back. So there will not, when we hit an if, there won't be any additional stack that's consumed when we evaluate the true and false position. Okay. And the most complicated one here for tail call optimization is that we have to change how we do our functions. And so I'm actually going to capture the value of this anonymous function instead of returning it. And JavaScript is kind of convenient here. I can take a function and I can just add arbitrary attributes to it if I want to. And I can still use that function and call it, but it happens to have some attributes, sort of like metadata almost, stored in that function that I can access later. And so I'm explicitly, I want to be able to use the captured values, the body and the parameters and the environment. I want to be able to use them explicitly later. So I'm capturing them when I define the function here. For the Python and Python and Ruby side, actually the Python and Ruby implementations, in the types file, there's a class that's actually defined that you can use for storing this. In JavaScript, it's a bit easier. Like I said, I can just store them on the function. Okay, and then here's the problematic place when I actually do a function call. If I have a function I've defined in mal, and then I call it, that results in something on the stack, and I don't have to do that. So in fact, what I can do here is after I've evaluated my arguments to my function call. Again, this is the function call case, not the function definition case. I can check to see, does this, yeah, so I'm capturing the function over here. Does this function have that attribute? And if it doesn't, I'm going to keep doing the other case I did. So there's really nothing we can do with core functions to save them from stack. But for our own functions that we defined, which is this case, there is something we can do. So what I'm going to do here, so this is going to be the case where we break and loop. So I'm going to redefine our evals local parameter AST to be the AST value that we captured from the body. I mean, it could have, probably a better name for this would have been body. And then, most critically, I'm going to basically replicate what I do up here for this function call. But instead of doing that function call, okay, so when we call a mal-defined function, rather than just executing it directly, calling it directly, the closure that it represents, what we're going to do is we're going to set our AST, update it to be the body that we captured before, and we're going to create a new environment, but we're going to set our evals environment to it. And so we're basically just clobbering the old environment that we don't need anymore, except for this here. The reference, oops. The reference that we captured to the environment is going to be the parent. So I will point out here that recursive function calls are creating new environments, but they're not creating stack. They're not creating an entry on the stack, so they're not going to stack overflow. You are going to use up memory if you recursively call mal functions. But it's pretty minimal, and if you're not actually using those environments anymore, they get garbage collected by these three languages anyways. So I'm creating a new environment here with the parameters bound to the arguments that we're called with, and then we loop. Okay, I know that was a little bit confusing. Hopefully you're getting that a little bit. I think when it'll really sink in is when you actually are able to implement this from scratch on your own, all the steps and up to this point, you'll be seeing, you'll run into a lot of errors that you'll fix, and that'll help you to understand what's really going on. But if this is implemented correctly, then, all right, so let me here have this somewhere. So I'm going to define an alternate sum to function. So this alternate function actually takes two arguments, an accumulator and the number that we want to sum down. And so this allows us to restructure this code so that the the recursive call to sum2 happens exactly in the if spot, right? So let me just define that and show you. Really? Must have done something wrong here. Let's see. That looks right. I must have done something. Oh, of course. I have to call it right. Sure, why not? So previously, the previous version we defined probably would have, in JavaScript, probably would have Stack Overflowed at about 2,000. But we're not, this is not creating any new calls on the stack. Every function call, every recursive function call is just updating that AST and EMV in your eval function and looping around. So there's no new function calls on the stack. It's one single function call on the stack that's just looping, doing this function. And so you can see that it works here. Okay. So let's see here.
It's called NAND because the missing second argument was just randomly from memory to computer.
I'm sorry, what's that?
First time you ran it, you got NAND. It's line.
Yeah, it's right. Yeah, it got a because I don't have any error checking in that case. What it got was a
Memory by interpreted.
yeah, it was a null or an undefined at some point. And it's trying to add to that, and so JavaScript, when you add to an undefined, it's NaN. So yeah, I forgot to set a parameter, so it's doing what I said. Yeah.
Is the setting the new environment inside of the tail call environment so you can like produce a stack trace?
Right. Yeah. So that's true. You have identified one of the problems with this approach is that one of the things we've lost is basically the stack. So that whole sequence of recursive function calls will look like one call if we have an error that throws that prints the stack out. Yeah. So if there are ways around that. You can actually save your stack where you are in your stack as another local environment in your eval. And so and then trap any exceptions that happen during that. And print your own stack instead of letting it bubble up to Ruby. So you can keep track of that if you want to. I don't do that here, so you're right. If I had an error that had a stack trace, you wouldn't see those recursive calls. So you're correct. That is one of the disadvantages of the naive approach. Okay, let's take a 10-minute break. Or you can stay and work on your implementation or ask questions if you like. Yeah, go ahead.
Lambda is closed on their environment, right?
What's that?
Lambda is closed on their environment, right? When you define a Lambda, it closes on its enclosing scope.
Yeah.
So in Mel, you actually handle, when you print a Lambda, essentially part of its definition, its definition. So you could print it, you could just copy paste it.
You're right. Yep. Yeah, that's exactly right. So the question is basically, so to give you an example here. So if I had a printer here, I mean, this is printing out the string representation of JavaScript. But the full implementation of Mel has a printer for functions, and it can look in the function and find the parameters in the body, and it can print out a representation of the function. But the problem is what you're not seeing here is you're not seeing a representation of the environment. And so because this is capturing this function, when I defined it, it's capturing a reference to the current environment that it was defined in. So you're right. If I had a string representation of it, you would be missing the environment information. So you're right. It's not a full round trip for that part of it. But.
For mine, I imagine that a Lambda can take either 2 or 3 parameters, and if it takes 3, it takes an explicit time.
Yeah, that's one option for implementation. Yeah. What's that?
Oh, she is.
Yeah.
Yep.